Okay, so next, the third method is Gauss Jordon Elimination method. Okay, so we will apply the same step, same procedure as we applied to Gauss elimination method. Okay, which is the second method just now that we have discussed. Alright, so write in the matrix form and then solve for x by writing the augmented matrix. Alright, so if the Gauss elimination method, we reduce A to REF form, the difference for Gauss Jordan is we reduce our A to RREF, or known as a identity matrix. We need to reduce this. Reduce A to RREF. Okay, where the most of the elements from the bottom part and the upper part will be 0. Okay. Right, so what we have done to Gauss elimination method, we just extend a little bit more, okay, by reducing the upper part to 0. That will complete the process, okay, the method, and it will become Gauss Jordan elimination. Alright, and the advantage of Gauss Jordan elimination, you do not need to transform your matrix back to system of linear equation. You don't need to do that, okay, and solve the equation, because when you reduce your matrix A to RREF here, or it will become identity matrix, you can instantly see the solution for the unknown, okay, where your x1 will be whatever value on the right side here. Same goes to x2, okay, for the second row, because the second row only has the coefficient for x2, so you can instantly see the solution for x2. And for x3, since only row 3 has the coefficient for x3, so you can instantly see the solution for x3. Understand? Okay, so I have explained this in the previous slide, but if you want to recall what is RRAF, you can go back to refer types of matrices. Okay. Okay, we'll be using the same example. Okay, for the purpose as I have mentioned before. Alright, so let's go to the next slide. And we just extend a little bit more what we have done to our matrix in Gauss elimination method. Alright. Okay, if you look at here, this is exactly the same step as we did in Gauss elimination method. Okay. Right. So same goes to the second operation, third operation, fourth operation, and the fifth operation. Okay, this is the last step where we stop for Gauss elimination method. Okay, so I have mentioned before, Gauss Jordan elimination method is the extension of GEM. Alright, why I say it is extension? Because you just proceed a little bit more by reducing this to 0, this to 0, and this element to 0. And then you will get RREF form. Okay, so we extend a little bit more. Now our aim to reduce minus 4 over 3 here to 0. So what we do here is we perform the addition of row 2 to to 4 over 3 of row 3. So that will reduce all the we reduce negative 4 over 3 in the second row to 0. Alright. So now you can see the pattern, right? Alright. So you can proceed more. Okay. Or you can stop. You should proceed more. Okay. Reducing this and that to 0. Okay. Till the end. Alright. But you can see already that this is your x3 equal to minus 2. And you have x2 here which is equal to 1. Alright. So this is what happened when we continue our elementary row operation and reduce it until we get identity matrix. Okay, RREF. Okay, so this is where I say that we can instantly see our solution for our unknown. Alright, so this is the column for x1, column for x2, column for x3. So for row 1, it is 0 for x2 and x3. So we know that our only coefficient for x1. So 1x1 equal to minus 1. Alright. And for our row 2, we have 0 for x1. We have 0 for x3. We only have the solution for x2 which is 1. Okay. For row 3, we have 0 for x1. We have 0 for x2, we only have coefficient for x3 which is 1. So all that instantly we can see directly that solution for x3 is minus 2. You see, these are all the same solution as we get from the first method and second method. Okay, so Gauss Jordon, which is the third method, should get the similar answer. The last method is Cramer's rule. Okay, so I have explained previously that the idea for Cramer's rule is using the determinant way. Alright, but for the first steps, okay, it is similar to the previous methods. Okay, the three previous methods. Okay, you should write your equation, okay, system of linear equation into matrix form. Ax equal to B, and then determine what is matrix A, what is matrix X, which is for the unknown, and what is your matrix B. Okay, here the notation, okay, that we will use is capital D, which is for determinant of matrix A. So determinant of matrix A here, we denote as D. Alright. And D must not be equal to 0. Okay, so determinant A, okay, cannot be equal to 0. Must be non-zero. Okay. Right, to solve for determinant of matrix A that we denote as D here, you can use the two methods, okay, to find the determinant, which is add two additional or two extra columns, okay, to at the back of your matrix here, so that you can multiply the diagonal, okay, and then minus with diagonal of the opposite direction. Okay, the second method is by using the minor cofactor. Okay, by expanding along your row or your column, any row, any column. Okay, so you can use these two methods. Okay. So to find the solution for our unknowns, okay, where here we in this example, okay, we will have three unknowns, which is our x1, x2, and x3. The formula that we will use, okay, that we call Cramer's rule, is determinant of the unknown x1, which is mean the column x1, okay, right, over determinant of matrix A. Okay, just now we denote our determinant of matrix A by D, capital D. So it is the determinant of the element, alright, divided by determinant of the matrix. Alright, and to find the x2, we find the determinant of column for x2 and unknown x2. We divide with determinant of matrix A. And for x3, we find the determinant of the last column, divide with the determinant of matrix A. Okay. Here, you can see the formula for each of dx1, dx2, and dx3. Okay, so dx1 is defined by this. Alright, so remember you have matrix A, you have matrix X, and you have matrix B, right? Okay, one column for matrix B. So what you do here for column x1, x2, x3, okay, for x1, x2, x3, alright, determinant of x1 here means you substitute the whole column of x1 here by your B, matrix B. Okay, so all your B here, the element of your B here, you write it, you replace the element of the x1, and you remain the last two column, which is column for x2, x3 remain. Okay, that define determinant of x1. And determinant for dx1 will proceed as usual. You can apply the two methods. Alright. Okay. For d of x2, okay, remain the column for x1 and for x3. Because you want to find the determinant of x2, column x2, so the whole element in x2, you delete it and replace it with b. Okay? And then proceed to calculate the determinant same way as you calculate the determinant for matrix A. Okay? Same goes to determinant for column x3 for your third unknown. Okay? What you do is your first unknown x1 will remain. Your second unknown will also remain. Okay? The one that is changing is the column for third unknown. So you should delete all the element for x3 here and replace it with b. So you get this matrix. See, this is x1 remain, x2 remain. This is what? This is b. Okay? And then find the determinant as usual. Alright, now once you have your determinant for the matrix A, determinant for x1, determinant for x2, determinant for x3, substitute everything into this formula. Then it will solve for x1, x2, x3. Okay? Right, I will skip this step because I have explained it in these steps, alright, in the previous slide. Okay, we proceed straight away with example. Okay, so again, by using the same example as we used in our first, second, and third methods. So for Cramer's rule, let us use the same example. Okay, so that we can see all the same methods should give the same answer. Alright, so same process, write it in a matrix form. When you write in matrix form AX equal to B, then you can directly determine what is your matrix A, what is your matrix X, and what is your matrix B. Alright. So next, find the determinant, okay, for matrix A that we denote as D. Alright. So in this example, okay, I use expanding along the first row. Okay, so if you choose to use this method, expanding along the row or the column, you must find the minor or the cofactor. Okay, so you must consider the plus minus sign. This is right. So the thing in the bracket here is the minor. Okay, all the coefficient in the front here. Okay, this is the element of first row because you choose to expand. I choose to expand along the first row. So I will use all the element for the first row. I will multiply my minor with the element of the first row. So this is where 0, 8, and 6 came from. Alright, and if you notice the plus, the minus, and the plus here, it is the sign for the cofactor, where we consider this as plus, minus, plus. And then back to, if you choose second row, it should be negative, positive, negative, positive, negative, positive. Okay, so in this example, the step is showing all at once. Okay, the minor and the cofactor, the expanding along, all in one step. Okay, because um, by using Cramer's rule, okay, when you want to find the determinant, okay, by using, don't waste time to find all the minor and all the cofactor. Okay, it is just wasting of time because that is not what the question wants here. Okay, because here the question wants you to solve by using Cramer's rule. Alright, so don't waste time to find the minor first and then find the cofactor and then find the determinant. Okay, because to find the determinant, you just need to choose one row or one column. Which row, which column, it doesn't matter. It's up to you. Alright, so to save time, you can do in one step, you cover all. Okay, you calculate all in one. Okay, in just one step. Alright. So you get negative 100 for determinant of matrix A. Okay, so remember what I said here. Alright, if the question didn't ask you to find for minor and for a cofactor or any other need that need you to calculate for cofactor, don't waste time to calculate minor and cofactor. Okay, unless if you use the first method, which is inverse method, to solve for the system, yes, you need to find minor and cofactor. Because for the inverse method, it involves with A inverse. A inverse, the formula is 1 over determinant of A times the adjoint of A. So adjoint need a cofactor. So for this method, you have no choice except calculate the minor and calculate the cofactor to get the adjoint. Alright, but for Gauss Jordon, Gauss elimination, for Cramer's rule, don't waste your time to calculate for minor and cofactor. Okay, so just straight away determine which column or which row you want to expand, and then find the minor and cofactor all in once. Okay. Okay, so the next step is we need, after finding determinant D for matrix A, our step is to find the determinant for our x1, x2, x3, or in this example we use x, y, z. Okay, so the column for x is this, and this is the column for y, this is the column of z. Right, so to find the determinant for dx here, okay, we will delete the columns x. Okay, so I choose this one. Alright, so this column, okay, all the element in this column, we delete it. Okay, so the second column and the third column will remain. So you see here, y and your z, column for y, column for z remain. All the element remain. But for column x, all the elements will be replaced by element in B. Okay, so minus 4, 18, 2. See? And apply the same way you calculate for determinant A. Okay, and you get dx equal to 100. Next, you proceed with dy. Okay, so since you want to find for determinant for y, so what you should do is now you will delete all the element in y, where element in x and z will remain. See, x is 0 minus 2, 1 remain, and 6 minus 6 minus 1 also remain. The one that is changing only the element in y, it will change with element in b. Okay, so b, put it here, minus 4, 18, 2. And then proceed as usual. Okay, calculate the determinant by using the usual method. Okay, and you will get dy equal to minus 100. Okay, lastly is finding the element the determinant for z. Okay, so same process. We'll delete the element in column z. Okay, so column x and column y elements will remain the same. So 0 minus 2, 1, 8, 4, 1 remain. So the only column that is changing is column z. Is changing by an element in column in matrix B, of matrix B. Okay, so minus 4, 18, 2, and calculate the determinant. Okay, so if you look at here, it always expand the first column. Okay, so this I expand the first column. Okay, find the determinant by expanding the first column. Same goes to this one. I expand the first column. And this one, I also expand the first column. Okay, it is not always the first column. You can choose the row and the column. Any row, any column is okay. Alright. So I would like to explain one more time. If you still cannot see, okay, solving the determinant, okay, finding the determinant in one way. I mean all in one way, all in one. Okay, right. So this, if you look at this is the submatrix. Okay, because when you delete the first row, okay, for the first element, you get the submatrix. Okay, you delete this and that. Okay, this is the submatrix, right? Okay. All the element in between the straight bracket here, these are all minor. Okay, this is all minor. Minor. That is minor. Okay. And when you delete for second one, which is this. Okay. So you will have 18, 2, minus 6, minus 1. Okay. That is the submatrix. Same goes to this one. This is the submatrix. Okay. So all the submatrix here are your minor. Okay. Your minors. Alright. So coefficient 6, number 6, number 8, number 4 here. These are the element of the first row. Because I choose to expand along first row. Okay. So I take all the element of the first row. This, that, and that. Alright. While the sign of minus here, plus here came from the plus, minus, plus. Okay. We can't see anything there because too much I delete this. Okay. This better now. Right. Okay. So the sign here, the minus, plus here came from here. Plus, minus, plus. So plus times minus 4 is minus 4. And then we plus with minus times 8 is minus 8. So plus minus 8 is minus 8. And this is from plus times 6 is plus 6. See? Okay. So this is the sign for the cofactor. Cofactor is about multiplying the plus minus sign, right? Okay. So the sign here represent the cofactor sign. Okay. Alright. And it will alternately, the sign will change negative in the second row. It will start with negative. Okay. Alternate sign from the first element. This plus, minus, then this plus, minus, plus. If you have 4 by 4, okay, let's say if you have 4 by 4, I just want to show. You have A, B, C, D, E, F, G, H, I, J, K, L. Okay, this is 4 by 3. 3 by 4. 3 by 4. So for this, it will be positive, minus, positive, minus. Okay, the second row will start with the alternate sign of the first element here. So minus, plus, minus, plus. Okay, and the third row, the sign for third row will start with the opposite of the second row here. So plus, it will be minus will be plus here, minus, plus, minus. Okay, so you don't continue from the end sign. Okay, if you choose to if you continue from the end sign, this will become positive, so it is wrong. Okay, once you have calculated all the determinant that you need, determinant for matrix A, determinant for each coefficient dx, dy, dz. Okay, so you just need to apply the formula, the Cramer's rule formula. Right, so for dx just now, we got 100 over negative 100, so x is minus 1. For determinant of matrix Y, it is negative 100 over with negative 100, you get 1. Okay, and for Z, for the determinant of Z, we got 200 divided by negative 100, you got minus 2. Okay, so the solution for x1, x2, x3 or xyz still the same as the previous method. Okay, so the Cramer's rule is the easiest method, right? But in exam, okay, if you were asked to find by using a specific method, please follow unless you got all 0. Okay. Okay, students, so we have done with all the 4 methods to solve for system of linear equation. Alright, but I do not want you to stop there because I have prepared like 7 exercises, okay, 7 questions here, okay, for you to do on your own. Alright, so please do these exercises to strengthen the skill on the 4 methods. Alright, so how do I help you? I will help you when you help yourself. Alright, so how do you help yourself? Help yourself by doing the exercises, because by doing the exercises, that is the only way you can find the weaknesses of you. Okay, from there you can realize which part you don't understand. Okay, and then from there you should ask me. Okay, so don't hesitate, don't procrastinate, ask me directly. Okay, I will help you, right? Because this chapter is considered as an uh, as a as an important chapter, right? Because all the question for your test 1 will cover everything in this chapter. Okay, so don't take for granted. This is test 1, which contribute quite a lot of percentage to your final mark. Alright, and your test 1 is just around the corner. Okay, if I'm not mistaken, it is scheduled to be in the first week of December. Once I confirm the date, I will let you know. Alright, so beside these exercises, I will also give you extra questions on the whole chapter. Alright, so please find it from your Google Classroom. Okay, I give the solution as well. I mean, not the steps, but I give the answer as your reference. Alright, but yeah, I'm here for you. Okay, come and come find me. Okay, we do it online. We find a way on how to help you. Alright, so for these exercises, my plan is to discuss these exercises during our online class next Tuesday. Alright, but if I couldn't do it, okay, I couldn't do it because of we still have one more part to finish, which is a part 5 for eigenvalue and eigenvector. Alright, if I find out that we have no time to finish that part, alright, I find a way on how to explain to you about the on these questions, alright. So don't worry, leave that to me. I find a way, alright. So your task now is do all the exercises. It is also good if you can try all the exercises in the textbook, especially in the application part. Okay. So whatever I said here, don't take it for granted. Okay. Whoever try, whoever um, is hardworking, you will get. Alright. So I stop my lecture here. Okay, even though I do not want to collect all this exercise. Alright, just do for you. Okay, just do for you. Don't do it for me. I have no advantage from you. Okay, you do it for yourself. Alright, thank you very much. Assalamualaikum.